Hello, I'm Veba, an EC student at MITK. I'm going to present the topic Discrete Cosine Transform for Image Compression. A digital image is essentially a two-dimensional array of pixels, and each pixel stores intensity or color information. In a grayscale image, each pixel typically requires 8 bits, meaning 256 possible intensity levels. In a color image, each pixel usually contains three components: red, green, and blue, each of 8 bits, totaling 24 bits per pixel. If we consider an image of size 1024 by 1024 pixels, that is over 1 million pixels. Every day, we generate and transmit enormous amounts of data, images, videos, audio, sensor signals, medical scans, satellite imagery. A single uncompressed 1080 pixel color image requires about 6 megabytes. 1 minute of uncompressed HD video can require several gigabytes. Without compression, storage costs would explode, network bandwidth would be insufficient, and real-time communication would be impossible. At its core, compression is about removing redundancy. Most real-world signals are highly structured. That is, neighboring pixels and images are similar. Audio samples change smoothly, and natural signals are correlated. Image compression techniques are broadly classified into lossless and lossy compression. Lossless compression reduces file size without losing any information, meaning the original image can be perfectly reconstructed. This is important in applications like medical imaging or legal documents where data integrity is critical. Lossy compression, on the other hand, allows some loss of information in order to achieve much higher compression ratios. The key idea behind lossy compression is that the human visual system is not equally sensitive to all image details. In particular, humans are less sensitive to high frequency components, such as rapid changes to brightness or fine textures. By selectively removing or approximating this less perceptible information, we can significantly reduce the amount of data required to represent an image while keeping the visual appearance almost unchanged. Compression algorithms exploit these properties. In general, most image compression systems follow a sequence of well-defined steps to reduce the amount of data required to represent an image. At first comes transformation, where the image data is converted from the spatial domain into a frequency domain using a transform such as the discrete cosine transform. This step helps concentrate the important information into a small number of coefficients. After transformation, quantization is applied, which reduces the precision of the transform coefficients and is the main uh, source of compression in lossy methods. Finally, entropy coding is performed to remove statistical redundancy by encoding the quantized coefficients efficiently using techniques such as uh, run-length coding or Huffman coding. Together, these steps systematically reduce both perceptual and statistical redundancies, resulting in a compressed representation of the image. One of the most important techniques used in lossy image compression is transform coding. Instead of compressing the pixel values directly, transform coding converts the image from the spatial domain into the frequency domain. In general, we can think of a transform as representing x of n as a sum of weighted sums of basis functions. In this equation, the ck are the basis functions and bk are the coefficients. The DFT In DFT, the ck of n are complex sinusoids. We know that complex sinusoids are very useful in LTI systems when a signal is expressed as a sum of complex sinusoids. The output is very similar to the input except the coefficients are modified by the corresponding values of the frequency response. For compression, we again express the signal as a weighted sum of the basis signal, but throw away the coefficients that are insignificant by setting bk to 0. If x of n has n values and only l values are significant, then we can say the save factor is n by l. This is the concept behind compression formats like JPEG, MP3, For image compression, we use discrete cosine transform over discrete Fourier transform. For the discrete cosine transform, we express the signal as shown below. The 1D discrete cosine transform converts a finite sequence of real numbers into a sum of cosine functions oscillating at different frequencies. Lower k values correspond to lower frequencies, higher k values correspond to higher frequencies. The first coefficient, k equal to 0, represents the average DC component. The coefficients xc of n are real values. It is important to note that discrete cosine transform is not useful when it comes to LTI systems, but very useful in compression because the coefficients are real. And additionally, using cosines can reduce the number of coefficients. MP3 audio uses this property of the cosine transform. If we have an audio signal, we first break it up into 26 millisecond blocks of n equal to 1152. We take this 1152 length signal, find the DCT, and store the significant coefficient and further encode into a sequence of bits. Important coefficients are chosen based on human perception of hearing. For example, if there are two tones of similar frequencies, the larger amplitude tone will mask the lower amplitude tone. So there is no need to store information about the second tone. The decoding process involves extracting the saved coefficients and apply inverse DCT to obtain an approximate representation of the original audio signal. Here we are plotting the cosine basis functions of the 1D discrete cosine transform for n equal to 8. Each curve corresponds to one basis function indexed by k. These curves represent the fundamental building blocks used by the DCT to express any length 8 signal as a weighted sum of cosines. The k equal to 0 basis is a constant while increasing values of k produce cosines with progressively higher frequencies, more oscillations across the 8 samples. Together, these 8 functions form an orthogonal set, meaning they are independent and can efficiently represent the signal in the frequency domain. In this demonstration, we compute the discrete cosine transform of a correlated signal and retain only a small number k of the lowest frequency coefficients while setting the rest to 0. We then reconstruct the signal using the inverse DCT. Despite using only a small fraction of the total coefficients, The reconstructed signal closely resembles the original. This visually illustrates the energy compaction property of the DCT. Most of the signal's important information is concentrated in a few coefficients. By discarding the remaining small coefficients, we achieve compression with only minor distortion, demonstrating the fundamental idea behind DCT based transform coding. The 2D discrete cosine transform can be used for compressing images. The idea is same as before, where we represent a 2D image as a weighted sum of basis images and set insignificant coefficients to 0. In the expression, we can see a 2D signal expressed as a weighted sum of cosine functions. The weights are the discrete cosine coefficients. The basis images are the product of vertical and horizontal frequency cosine. In this plot, we can see the basis images for the indices k and I for n equal to 8. Each image is 8 by 8. We have 64 possible images that represent the 64 pixels in an 8 by 8 image. In the first column, we see the vertical cosines and the first row contains the horizontal frequency cosines. The other entries contain product of horizontal and vertical frequency cosines. The plot shows the 64 orthonormal 2D DCT basis images for an 8 by 8 block. Each small square represents one pair of frequency indices ik, where k controls the vertical frequency and I controls the horizontal frequency. The top left image 00 is the DC basis and appears as a constant gray block, representing the average intensity of an image. As you move to the right, the patterns oscillate more rapidly in the horizontal direction, meaning the horizontal frequency increases. As you move downward, the oscillations increase in the vertical direction, meaning the vertical frequency increases. The bottom right corner contains high frequency patterns in both directions and looks like a fine checkerboard. Together, these 64 patterns form a complete orthonormal basis, so any 8 by 8 image can be represented as a weighted sum of these basis images. Consider this 8 by 8 image which has a horizontal edge alongside. We have plotted the DCT coefficient and we see that they are all concentrated at k equal to 0, that is along the vertical frequency. Clearly, there is no variation in the horizontal frequencies of the image. The concept of image compression is to use only a portion of the DCT coefficients. Here we are using only the first 4 coefficients. When we reconstruct the image using only 4 DCT coefficients, we do a pretty good job of reconstructing the edge. And since we are using only 4 DCT coefficients instead of 64, we have a compressed factor of 60. Let us take another example, this time a proper grayscale image. On the left, we see an original grayscale image. On the right, we see its 2D DCT coefficients displayed in log scale. Notice that one of the bright values are concentrated in the top left corner of the DCT image. This region corresponds to low frequency components, which represent the smooth variations in the image. As we move towards the bottom right corner, the coefficients become less small, representing high frequency details like edges and noise. This demonstrates the energy compaction property of the DCT. Most of the important visual information is packed into a small number of low frequency coefficients, which is why DCT is highly efficient for image compression. Here we progressively reconstruct the image using only the top left DCT coefficients, which represent the low frequency components. In each step, we keep only a small block of coefficients and set the rest to 0 before applying the inverse DCT. Here, when we use only 8 by 8 coefficients, the image looks blurry, but still recognizable. As we increase the 16 by 16, 32 by 32, and 64 by 64, more details start appearing and the image gradually approaches the original. This shows that even a small fraction of the total DCT coefficients is enough to preserve most of the visual information. It clearly demonstrates how DCT enables compression by allowing us to discard many high-frequency coefficients while maintaining acceptable image quality. Here, we compare the DCT and DFT of the same image. The DCT magnitude plot shows that most of the energy is concentrated in the top left corner, meaning low-frequency components dominate. In contrast, the DFT magnitude plot shows energy distributed symmetrically around the center due to complex exponential basis functions and periodic assumptions. The DCT uses only real cosine basis functions and assumes even symmetry, which reduces discontinuities and boundaries. As a result, the DCT achieves better energy compaction than the DFT. Here is why image compression standards like JPEG prefer DCT over DFT. It represents image information more efficiently with fewer significant coefficients. In conclusion, the discrete cosine transform (DCT) is a powerful tool for representing signals and images in the frequency domain, enabling efficient compression by concentrating most of the signal's energy into a few coefficients. The 1D DCT helps analyze temporal and or spatial signals, while the 2D DCT extends this to images, forming the foundation of modern image and video compression standards. By retaining only the significant coefficients, we can achieve substantial data reduction with minimal perceptual loss. This makes DCT widely used in applications such as JPEG image compression, MPEG, and H.264 video coding, audio compression, and other multimedia processing tasks where reducing storage or transmission bandwidth is essential. Thank you. Here are useful references to learn more about DCT.